So now we're going to go talk about the meat of our stuff, which is really gradient descent. So I'll send this out too on through the channel. But gradient descent, sorry guys. Yeah, this leads us into gradient descent. And gradient descent is basically this really great tool. We use derivatives to basically figure out how steep things are and basically figure out how can we minimize this error. And we use something called like the cost function. And it turns out in linear regression, we'll talk about what is the cost function, what does that mean? But you can actually define cost functions in a lot of different ways for different algorithms. And this is why it makes it really powerful for machine learning, because now we can have a powerful way to describe basically what we're trying to minimize, and we can use gradient descent to go down. If you finish end of section 13, the curriculum kind of goes through this idea of like linear regression and trying to figure out what's the best line of fit with basically using matrices system of equations. But it mentions that basically saying, hey, we could technically do this for very, very large systems. So let's say you have like 50 variables, you know, you could try to solve the system of equations, but the efficiency to solve that kind of matrix that we saw from section 13 is just really, really inefficient. It's not a really great way to approach it. I could be wrong here, so if someone else knows better, let me know. But I think it's something like solving systems of equations goes up to the power of 3 for large systems. So it's pretty fast until you hit a large number, which in data science, we're hitting large amount of variables, a large number of features. So it just ends up being not very good in that sense. So we can do something called gradient descent to basically, I like to say it's like, we keep estimating until we get better and better, until we say, yeah, that's good enough. That's kind of what gradient descent's really doing. So I kind of said a little about the motivation of why we do from linear regression, but I'll just go ahead and start running this stuff. Oops. Oh, and I also put that on GitHub too. That way you guys can access it even if we change things up. That's new. But anyway, so the first thing I'm going to do is just show you what happens if we try to create, a linear regression. So right here, I'm basically just creating some random data. Okay, so you can see here, I'm just giving it a seed. This is actually directly from the curriculum, so note that that's just what I'm doing. But I'm creating some random data, okay, and I'm making sure, I think it's like, this is 30 data points, right? And we're making sure we're getting a random normal. So that way it's just kind of randomly around what we want. And I gave it this equation. It doesn't really matter what it is. It's just to produce terms. And then what we can do, we can actually plot a regression formula, right? We can just say, you know what? Instead of trying to figure out what the regression line is, let's just try to draw a line and see what happens. So I just wrote this formula right here, which is kind of derived from the curriculum. But basically, I'm taking in my x, which will be some point, right? B1, right, which is just going to be my y-intercept, and my a, which is my slope. In this case, I put it for 50, but I could have changed it however I wanted. And we're just plotting it out. So if we plot this out, we can actually see our regression line and the data points. And for this regression line, not too bad, right? It could have been a little bit better. For example, let's say I go ahead and try to change the slope to, I don't know, 40. Let's see what that does. Like, that's no good, right? A little off. It's like, well, maybe I need to raise it up a little bit. Maybe I need the y-intercept a little bit higher, right? So maybe it's like, I don't know, 5 or 4. It's like, not quite. It's like, oh, maybe I need to go like 50 here. Like, okay, that's kind of better, but I could have probably done a little bit better. Maybe like, 2. And you can start seeing like, okay, I'm getting better and better, but then how do I know when I'm the best, the line of best fit? That's really what I'm trying to look for. The smallest error in here like this. And so the real part is like, how do we analyze a regression line? How do we know if it's good or not? Like we can look at it, but what do we do to figure out if this line is a good fit? Does anyone remember? Any ideas?
Differentiate.
Regression, right? So one thing is we can talk about is our residuals, right? Basically, we can say how far is this point, if I draw this out, how far is this point from the line, right? And how far is this point from the line? And how far is this point to the line? And how far is this point to the line? And so on and so forth. And if you guys remember, we don't just look at just the residuals, we do the square of this residual. So we'd square this. So you can imagine all these like little squares forming around the line, the linear regression line, okay? And then we can add up all of these squares, okay? The sum of all of these residual squares, or the residual square sum, RSS, okay? So that's usually how we determine, say, oh, how we say if the line is good or not. That's kind of like what we can, if we can make this as small as possible, then we know our line's probably, it's the best fitting line we could possibly do. All right. So we can actually do the code on this. And let me clear that out. So you can see right here, I just wrote a few things. And then again, this comes from the curriculum. So you'll see it again as you go through section 14, or if you've already gone through section 14, this looks familiar. But I find the errors, right? And the errors are basically just saying, how far away are my y values from the line, right? That's my little, I drew that little line from the point to the line. And that's what this part is. My squared errors, I basically am saying, okay, let me go ahead and figure out, you can see I take this, what's it called? The function of the errors, and I'm just squaring those errors. Okay, in this case, the curriculum has a round to, so that way it's not like 0.054321 or whatever. We can just round it off by 2. We just need to get about, right? And then we can do the residual, right? The residual sum squares, so the RSS. So you can see right here, I just add up, I'm summing up all of the squared errors for all of those x values and then y values. So basically I'm just adding up on this, and that's what all the code is doing. It's kind of what I described. So now we can do is, okay, and this right here, you can see we're just getting different zeros right here. We're iterating through this range so we can get basically all those points. And in this case, I copied this from the curriculum too, so that's why this is a little different. I'll keep it there for now. But basically this is testing against this line, this M. But let's do it against our line. Our line was a slope of 2, okay? Let's try a slope of 2. Oh, sorry, not a slope of 2, y-intercept of 2. Okay, and you can see here, we now have the plot of all our different residuals right here. And it's all we did right here is our slope of 2, and we are just iterating over different values for our slope. Okay, so that's what this value right here is. So I could have also put this as A. See, same thing. So we see here, it's like, okay, if I have the slope, or I have the y-intercept as 2, keep that constant, and just adjust the slope back and forth, basically I can start seeing, oh, if I have a slope of about 40, like we saw in the very beginning, errors are really far off. But as I come down further and further and further to about 51-ish, okay, I can see, oh, the error is pretty small right here, right? And it hops back up, okay? So basically going further away. So you can kind of see, like, I'm kind of adjusting that part. So if I look at, let's say, a slope of 40, right? That's my line, and I'm going to trace it out with here. So you can see, like, this is my line right here, of 40, and let's go ahead and try, it's at about 58. You can see that's my line of 58. And I think it showed that about 51 was my line of best fit. So you can kind of see, it's like, oh yeah, I can see that. It's not too bad. And you can see this line, this bottom line, which is the slope of 40, is really bad. This line is really good. But you can kind of see, like, oh, this is what we keep adjusting this line. Now, you might notice, though, what might be an issue with us doing it this way? What's one thing that we didn't try to test out? Because we're checking out this slope, right? And we can eventually find what the minimum error is. We can try to figure out what this part is. But what didn't we change?
Intercept.
We didn't change the intercept, right? Maybe that intercept, maybe there's a better intercept than this one. I don't know, right? So we'd have to figure out, well, okay, what's this intercept to? And that's actually ends up being when we start doing gradient descent in multiple dimensions. And so the idea here, though, is that's like, well, okay, if we were over here and the error was really, really bad, we'd want to say, oh, let's adjust it so it's better. And let's adjust it again for it's better and better and better and better. And once we got down here, you want to make sure you kind of like be really fine-tuned, like just adjust it a little bit and a little bit and a little bit. Versus if all the way up here is like, whoa, that's really off. I need to change it significantly. And that's what gradient descent really does, except we're doing it mathematically, meaning that it describes, we can mathematically describe how far should we change. So this leads us into our gradient descent. So you can think of this like stepping down a hill. And there's a great picture, I think, in, oh, maybe not, I can't think of it now. I was looking at the curriculum, but Here's a good picture of it. But same cost curve right here. And you can see this is our three-dimensional part. So you can imagine 3 dimensions too, as we need to change both the intercept and the slope. But the main thing I want to talk about is like, we can just step down the hill. So you can imagine, like I said, if you were just looking at just the error, you weren't looking at the line itself, you say, well, my error is really bad up here, okay? And you say, well, if I know that this function is down here, it's like, well, I just need to go down like here and really down here and really down here, okay? The problem is that if I took, let's say, big steps, like I take big jumps each time, you can imagine I might accidentally skip over that minimum, right? That minimum is probably right about here. So what we can do with gradient descent, we can say, well, let's judge it on how steep it is. If it's really steep, okay, that means we probably have to get, take some big steps, okay? And then if it's not so steep, we can actually take smaller steps. We can take these little tiny steps going through here. And sometimes you might jump over it, but we just gotta say, oh, wait, I'm going back uphill again. Let me go back down. So this is actually how gradient descent works. And we just talked about how we can find steepness. What do we use to find steepness? We just talked about in the other part. I guess it starts with a D.
Differentiation.
Differentiation, derivative, right? We can take the derivative. If we know how the derivative right here, we can think of our f prime, right? If we know what f prime is, we know what derivative is, we know how steep it is. So we know how far to go down, okay? And that's really what gradient descent is. Gradient descent really is just using differentiation, taking derivatives, to find how steep we have to go down this function here. And this is really what we call our cost curve. This is basically our cost function. Basically saying, what is going, like, what are we trying to minimize? And we're trying to minimize the error. We're trying to minimize RSS. So this is like the cost of the function, okay? I'm not, to be perfectly honest, I'm not quite sure why you call it cost. It seems counterintuitive to me, but the way I kind of think about it is like, it's the cost of using that, like how bad that function is. And so that's really saying, well, how bad is that function? We want to minimize that. So we say, how bad is that function as we change the slope? How bad is that function when we change the intercept? And then we can also do, how bad is it when we change both? And that was the picture that I showed really briefly. Oops. Really briefly right here, is that you can see it's a 3-dimensional part because we have our slope, our intercept, 2 dimensions, but then also we have what's the cost, basically how bad is our function. And you can see basically it's a flat sheet in this 3-dimensional space. So you can kind of imagine if you were like on this sheet and you're trying to, and you were like blindfolded, you're like bird boxing your way through here, is that you can try to figure out, okay, how steep do I have to go? You can kind of feel around with your foot saying, okay, this is much steeper. Oh, that's clearly uphill. Okay, kind of lean back. Okay, it's much steeper this way. I'm gonna go this direction. And you can eventually, hopefully, if you kind of keep taking bigger steps to smaller steps, you eventually find the smallest point right there, okay? So any questions on that concept of gradient descent? And really that's literally all gradient descent is. Okay, so what's nice, like, okay, cool. You say, cool, Victor, like you described gradient descent, but how do we do it, right? So first of all, we can do it for higher dimensions like we showed, but we use something called the gradient function, okay? And this right here is an upside down triangle. I think it's a nabla, I could be wrong. But you'll see this a lot, and notice that this right here basically is finding our derivative for each, what's it called? Finding our derivative for each variable. So if we have like a function that's dependent on x and y, just like we have a function here, this function is not really, our error, our RSS is not just based on the m value, not based on the slope. It's also based on the intercept. So we actually have 2 variables here. You can think of it like x and y. We have to take those partial derivatives and basically figuring out that part. And notice that there's a negative. The reason why we find a negative is that if I find the slope right here, okay, and I find the slope is down this way, right? I actually want to go the direction of, I want to go in the opposite direction of what the slope is saying. Oh, it's going this part. I want to go downward. I want to go down towards the minimum. And that's why we have that negative part in there, okay? So like, for example, the slope is up here is positive. I actually want to go in the negative direction. In this case, the slope is negative. So I actually want to go, well, that's not true. I want to do it in the opposite direction. It's because it's on the next part. Yeah, okay. So cost function, gradient, that's how we do it, okay? So I want to show you guys briefly on how you actually do calculations, how you find partial derivatives. And one thing in the curriculum, I haven't seen their notation before, which is kind of strange to me. They'll write the partial derivative as df dy of the function, but I haven't seen it like that before. I almost wonder if it's a typo. I have to ask the curriculum people. But I usually see it as the partial, which is like kind of this special d right here. Usually it's just labeled as partial, but this lets us dy of x, or I'm sorry, of f, okay? So let's start off with a, oops, I have too many annotation tools here. Okay. So let's start off with a function. So, oops, I don't want that. I want our generalized f of x. And this time we're actually going to have a function that's dependent not just on x, but also on y. Okay. And what I mean by that is that depending what you put in x, and what you put in y, you can think of this as, like, for example, the slope or in the y-intercept. As we change the slope in the y-intercept, our thing will change. So for example, let's just put something like y plus x times some numbers, let's say times 2. Okay, squared. Okay, this is actually really easy for a partial. If we have our partial with respect to x, and I'll just put f, right? What this is just going to do is you're going to treat everything that's not an x essentially as a constant, right? So in this case, a derivative of a constant is 0. Derivative of 2x squared is just 2 times 2, 4x. So our partial would be 4x. Our partial for y of f, okay, is going to just be treating everything that's not a y as a constant. So in this case, 1, and then 2x squared, that's a constant in our minds because we're only caring about y, so plus 0. So in that case, it just changes by 1, or it's just 1, okay? So that means basically the change in y is consistent versus for x, it's actually, it changes depending on x. So the rate of change changes, okay? So that one's actually really probably the simpler of the ones that you'd end up doing. But if we want instead to do something a little more complicated, which most functions that are f dependent like this, you might have multiple put together. So if I have something like y times x squared, like this, now if I take the partial derivative, let's take the partial of y first. Okay, when we take that partial of y, what I'm doing is I'm going to treat x as a constant. So you can kind of think it's like saying, okay, let me take the derivative with respect to y, partial derivative, where y times, you can think of it some constant, right? Since we don't really care about that, right? We're not going to change it. Like if you imagine this as like some letter a, or if you imagine, I don't know, I'll give it a number. So let's give it like 2 times y. This derivative would just simply be 2, right? But of course, it's not actually 2 that we were caring about. Instead, it was x squared. So the partial derivative of f in this case is just simply x squared. Okay? So the partial of f with respect to x, we do something very similar. In this case, we treat y as a constant, right? So anyone take a guess of what this would be now when we take the partial of x, or of f?
2y.
2yx, good. And that's exactly right. Because we can just treat y as the constant, 2yx. Okay? So now this allows us to basically figure out these parts. And the reason why we do partials is because essentially when we're trying to climb down this three-dimensional surface, what you're really doing, what you're going to do, you're not going to be able to figure out what the specific downward is. We basically say, okay, I'm at this point in the hill. So maybe I'll draw this out a little bit. If I'm on the point of the hill, let's say right here, okay? I want to figure out what the steepest way is. So instead of figuring out like, well, this might not be along X or Y, it might be kind of like in a diagonal position, right? Which is the steepest way. So the way we can kind of split this up, we say, okay, what's the steepest direction in the X direction? So let's say in the intercept direction on here, what's the steepest direction? Is it to the left or is it to the right? It's like, oh, it's kind of to the, in this case, we'll say, instead of looking up the hill, it's to my left, right? And I say, okay, what's the steepest direction in the Y? Well, this seems pretty obvious. It's going to be, in this case, more onto my, behind me, okay? And so we'll move down in this direction. We'll move a little bit off to the X direction, a little bit in the Y direction, and move to right here. And so that way we can just kind of keep going through. Say, which is the steepest direction? Oh, okay, well, the steepest direction this way, and maybe not so much in this X direction. And so you move down to this point right here. So you kind of keep going down, and eventually, as your slope gets smaller and smaller and smaller, okay, you'll move less and less and less, okay? Now, one thing still is that if we use just the pure derivative of it, we might still skip over it because our slope is too steep. So for example, if our slope is really, really large, let's say a slope is like, I don't know, let's say 50 or something like that, we might actually completely skip over, like say, oh, well, 50, we're gonna go over here, and you go in that direction, you end up past the minimum. So we'll do something called a learning rate. So we'll actually multiply it by some, usually it'll be denoted as alpha, okay? And we're multiplying it by basically this gradient right here. And that is our learning rate, basically saying, well, if the derivative is too big, we don't want to accidentally skip over it. And usually this number, depending on the context, but usually you'll see it like 0.01. That's usually a good alpha. If you make it too small though, why might you not want it too small? Anyone take a guess? Remember, our alpha is kind of like how big of steps how we measure everything. Good, John, it would take forever, right? If you made alpha really, really small, it would just like take forever. You'd be like, it's like, oh, this huge derivative, this huge slope, but you'd still be like walking really slowly, right? And then that translates to the computer taking forever for us to walk down that hill. Okay, cool. Any questions about anything I talked about this guy? And you can see they have a little example here. I didn't really like this one as much, but it's fine. Okay. They also, just kind of warning in the curriculum, they talk about, so this is what I was talking about right here. I'm not quite sure. They're talking about the partial derivative, but I wouldn't write it as df dy, if you guys can see that. I think usually in the literature and stuff like that, what you usually see will be like something d, like that. That's how I've seen it classically. So I'm not quite sure what it's trying to show right here. But, and then you would say, okay, you get the derivative of this, you can turn it into a full derivative, and then saying of y. So just be aware, I guess, that the notation is a little different. But one thing here, they kind of split up the different graphs. You can also think of like partial derivatives as saying like, look at just a two-dimensional slice instead of looking at three-dimensional and stuff like that. And of course, when you get to higher dimensions, it's not going to be three-dimensional. It's going to be much higher, like 5, 6, 7, 20-dimensional. That obviously makes it a lot harder for us to visualize. So you can kind of think of like we're taking the partial derivative along a, what's it called? A slice where we get just two dimensionals because we're a little easier to visualize those things. Okay. All right, guys. So that kind of finishes up what I have. Obviously, the curriculum goes through a lot more detail, particularly about, what's it called? Actually putting into code of what's going through. But the concepts are all there. And I think that's an important part to know is what exactly is gradient descent, because sometimes the math can be very intimidating where you're looking at all these different values and stuff and it turns out, oh, it's actually not that bad of an idea. We're just basically going down a mountain, except it might be higher dimensional. It might not be three-dimensional or something like that. Sorry, that's my dog. Okay.